ఓకే. విల్ స్టార్ట్ 2 మినిట్స్‌లో స్టార్ట్ చేద్దాము. 7:40కి. Okay, we'll get started. So far we have discussed about the first law and second law for closed systems. So first law for closed systems ఏంటి? du is equal to dq plus dw when kinetic energy and potential energy are neglected. And second law mathematical form ఏంటి? Delta S total is always greater than or equal to 0. Now let us look at the first and second law for open systems. We'll start with the first law. Open systems ki first law ఇలా డిఫైన్ చేస్తారు. d by dt of mu cv plus delta of h plus u square by 2 plus gz into m dot is equal to q dot plus w dot. ఇది fs. Subscript is fs. So let us understand each term of this equation. Let us say this is our control volume. This is our control volume. Control volume ante a volume of the fluid which is chosen for study. ఈ control volume ki let us say there is one inlet and we have one outlet. There can be any number of inlets and any number of outlets. Mana case lo we have two. So d by dt of mu cv, this is the accumulation term. Accumulation term ante the rate at which the internal energy of the control volume is changing. So ఈ control volume ki oka mass untundi and it will have some internal energy. The rate at which the internal energy of the control volume is changing is d by dt of mu cv. Is the first term clear?
Yes, sir.
Okay. Now let us look at the second term. Second term lo enti delta. Anytime you see delta ante it is out minus in. సో అవుట్లెట్ స్ట్రీమ్ ఉంది కదా, ఇప్పుడు ఈ అవుట్లెట్ స్ట్రీమ్ని 1 నేమ్ చేసి ఆర్ ఇన్లెట్ స్ట్రీమ్ని 1 అండ్ అవుట్లెట్ స్ట్రీమ్ని 2 అని నేమ్ చేస్తే ఈ డెల్టా టర్మ్ ఏమవుతుంది? ఇఫ్ యూ ఎక్స్పాండ్ ఇట్ విల్ బి h1 ప్లస్ u1 స్క్వేర్ బై 2 ప్లస్ gz1 into m m
M dot mass flow rate.
right m sorry ఇవన్నీ 2 బికాస్
Yes, అన్న 2 కదా, 2 - 1 అన్నావు కదా, అవుట్లెట్
2
-2.
- 1 కాబట్టి అన్ని 2 m2 డాట్ మైనస్ h1 ప్లస్ u1 స్క్వేర్ బై 2 ప్లస్ gz1 ఇంటూ m1 డాట్. దీన్ని షార్ట్ నొటేషన్లో ఇలా రాస్తాం బికాస్ ఇఫ్ యూ హ్యావ్ మోర్ దెన్ లెటస్ ఇంకా చాలా అవుట్లెట్స్ అండ్ ఇన్లెట్స్ ఉన్నాయనుకో ఇట్ ఈస్ కన్వీనియంట్ టు యూస్ దిస్ డెల్టా నొటేషన్. And this q dot plus w dot, this is rate of heat transfer to the control volume, and w dot is the work done on the control volume. So now all the terms are clear kada. Okay, and e term ni let us further h ante enti, h is the enthalpy of the stream. ఇప్పుడు స్ట్రీమ్ 1 ఉంది, హెచ్2 అనేది ఎగ్జిట్ స్ట్రీమ్ ఎంథాల్పీ, హెచ్1 అనేది ఇన్లెట్ స్ట్రీమ్ ఎంథాల్పీ, u is the velocity. So this term represents the kinetic energy. Excuse me, give me 1 minute. Sorry for the disturbance. Let us continue. So are you clear with each and every term of this energy balance equation for open system? Or are there any doubts?
Yes, అన్న clear అన్న.
Okay. Once you are clear, we'll move into a very important application of this equation. So I'll write it down once again. D by dt of mu cv plus delta of m dot into h plus u square by 2 plus gz is equal to q dot plus w dot. Now we come across many steady state flow devices. Steady state flow devices in chemical engineering. What are some of the examples? You have steady flow in a pipe or a nozzle or a compressor. You have a pump. You have an expander. So all these, the working of all these can be understood using this equation, because you know these are open systems. So what is the fundamental definition of an open system? Open system means mass can enter as well as leave. So mass transfer can occur across the boundary of the chosen volume, control volume. So out of this, the most important ones are compressor, pump, and expander. So for a compressor, pump, and expander, since we have mentioned steady state, so at steady state, what happens to this term d by dt of mu cv?
At steady state, it will be considered to tends to 0 అన్న.
It will be 0. So this will become 0. And what we do is for pump, compressor and expander, we neglect the changes in, if we neglect the changes in kinetic and potential energy. So in most of the cases this happens. You should be careful in choosing how to apply the equation. So if you neglect these both, if these both terms tend to 0, and you are assuming adiabatic operation, if the operation is adiabatic, what happens to this term?
0.
0. So in this case, the equation simply reduces to delta of m dot into h is equal to the work done. So you can calculate the work done by a compressor, pump, or expander if you know this. Now further simplify. For example, take a compressor. So this is a compressor. You have one inlet stream and one outlet stream. So if the flow rate of inlet stream is m1 dot, what is going to be the flow rate of outlet stream under steady conditions?
M1 dot.
Right, m1 dot, which means you can write this as m1 dot into, and the outlet stream enthalpy is h2, inlet stream enthalpy is h1. m1 dot into h2 minus h1 is equal to work done. Right? Is this clear how we arrived at this equation?
Sir,
Okay. Now this is the same equation whether it is a pump, whether it is a compressor, or whether it is an expander. A compressor is used for gases to increase the pressure. Pump is used for liquids, whereas an expander is opposite to a pump or compressor, which means for pump or compressor we need to supply work, whereas an expander is going to gives us work as the output. So there are expander operates on gases or vapors. Sometimes you also hear the word turbine. So a turbine is nothing but an expander which operates on water vapor. Now let us look at another steady state flow device called throttle valve. Throttle valve. So the throttle valve is denoted by this symbol. Oh, before we move into the throttle valve, let us write the energy balance equation for the throttle valve. For the throttle valve, the energy balance equation is going to be so once again the unsteady term is going to be 0, similar to the previous energy balances. Then the kinetic energy term 0. Then if you put the potential energy term to 0, you will finally have m dot into h2 minus h1 is equal to q dot plus w dot. Now the throttle valve, if you assume adiabatic operation, this will become 0. And you also obtain no work from the throttle valve. So work done is 0, which means h2 is equal to h1. So what is a throttle valve? A throttle valve is a isenthalpic device. What does that mean? The enthalpy of the outlet stream is equal to the enthalpy of the inlet stream. So is this clear? Why the throttle valve is an isenthalpic device? Okay. Now, since we are done with the first law for open systems, let us look at the second law for open systems. Second law for open systems. So if you recollect, the first law is based on the principle that energy is conserved. Whereas the second law is based on the principle that entropy is not conserved. Is not conserved. The entropy of the universe keeps on increasing. So for an open system, the entropy balance is written as follows. Again, you'll have the similar term d by dt of MSCV. So the unsteady term plus delta of S into m dot over the control surface minus, plus rate of change of entropy of the surroundings. So this superscript T implies total entropy. Whereas if there is no superscript, this is specific entropy. That means entropy per unit mass. This is also entropy per unit mass. Whereas this is total entropy. So you have dst by dt of surroundings is equal to Sg dot. Sg dot is the rate of entropy generation. And this rate of entropy generation is always greater than or equal to 0. It is equal to 0 for an reversible process. In all real processes, it is greater than 0. So clear with this law, the second law for open systems?
Yes or no?
Okay. Now this term dst by dt can be further simplified as summation of qj dot by t sigma j. Now let us understand what this means. So let us say this is our control volume and there is some part of the control volume which is exchanging heat Q1 at the rate of Q1 dot with the surroundings, and the surroundings is at a temperature of T sigma 1. Sigma stands for temperature of surroundings. And there is another small part of the control volume which is exchanging heat with the surroundings at the rate of Q2 dot. And the surroundings at this point is has the temperature of T sigma 2. And let us say there is another part of the surface which is receiving heat at the rate of Q3 dot. It is receiving heat from the surroundings which is at a temperature of T sigma 3. Now, can you tell me what is the rate of entropy change of the surroundings because of this part, because of this heat transfer? The rate of entropy change is q2 dot by T sigma 2. Similarly, in this case, this is minus because heat is being transferred away from the system. Similarly, in this case, you have q1 dot by T sigma 1. And in this case, you have q minus q1 dot. In this case, you have q3 dot by T sigma 3. Is this clear why we wrote it as Q by T?
Yeah.
Because when ds is equal to dq by t, when is this definition valid? ds is equal to dq reversible by t. This definition is valid for a reversible process in a closed system. There is another important point that whenever you have a system which is transferring heat with a reservoir, and the reservoir is at some temperature T sigma, and the heat transferred is Q dot, irrespective of whether the heat transfer is reversible or irreversible, the entropy change of the system is given as Q by T. It does not matter whether the heat transfer is reversible or irreversible. The entropy change is always given as delta S is equal to Q by T. Is this point clear? This is a special case associated with heat transfer. Whenever there is heat transfer, and immaterial of whether the heat transfer is reversible or irreversible, the entropy change is as a result of this heat transfer is given as Q by T. So if we apply this into the second law for open system, we are going to end up with delta of S into m dot Fs plus d by dt of MSCB minus summation Q j dot by T sigma j is equal to rate of entropy generation. This rate of entropy generation is greater than or equal to 0. Now let us do one thing. If we apply this second law for a compressor, if we apply the second law for an ideal compressor or an ideal pump or an ideal expander, what is going to happen? We have an insulated ideal pump, compressor or expander. By ideal I mean reversible. It is operating reversibly. So if it is insulated, what happens to the Q dot J terms?
They will be tending to 0.
They will be 0, right? What happens to rate of entropy generation? Will it be 0 or will it be greater than 0? Because I said reversible entropy generation, there will be no rate of entropy generation. This term will become 0. And if I add another thing, if I say steady state operation, what happens to this term?
0.
This term will become 0. So now all you are left with is this term. And since all these have only one inlet and one outlet, inlet flow rate will be equal to outlet flow rate. You will get m dot into S2 minus S1 is equal to 0. which implies S1 is equal to S2. So these devices are called isentropic devices. So now you have pump, now you have expander, compressor, pump. All these three are isentropic devices. And then you have a throttle valve. A throttle valve is an isenthalpic device. Isentropic means S1 is equal to S2. Isenthalpic means H1 is equal to H2. So these are some things which you need to remember. Now is everyone clear with this? Or do you have any doubts? Because we'll be solving a problem based on this concept. Okay, then let us solve a problem. I have sent the problem in the WhatsApp group. I hope everyone has read the question. If yes, then we can go ahead with the solution. Okay, done reading?
Yes, Anaya.
Okay. So before we solve this problem, let us look at phase diagram. So phase diagram for a pure substance. Phase diagram for a pure substance is going to look like this. Now, here you have the solid region. Then here the liquid region. And this is the vapor region. Pressure on the y-axis and temperature on the x-axis. And this red curve represents the vapor liquid equilibrium line. So at any point on this line, you have coexistence of vapor and liquid. Similarly, this yellow colored curves shows solid liquid equilibrium. And the blue color curve shows solid vapor equilibrium. Now, beyond this point, there exists a point. Beyond this point, this is known as the fluid region. And above this temperature, this region is known as the gas region. So in the this fluid region is also known as the supercritical fluid region. Now this is one way to study the phase diagram. There are several other phase diagrams as well. For example, we have the TS diagram. So in the TS diagram, you have T on the y-axis and entropy on the x-axis. We have this is the solid region. Then in this gap you have solid plus liquid, and then you have a dome. So all this is the liquid region, and inside the dome you have liquid plus vapor, and this entire thing is again the vapor region. So you can see that the liquid plus vapor region is the area under this dome is a two-phase region which consists of liquid plus vapor. So whenever you are, let us say you are at this temperature, at this temperature you have pure vapor, and as you keep lowering the temperature, you are going to enter this dome, two-phase dome, and as you reach certain temperature, you're going to have part liquid and part vapor. So you have the two-phase region here. Now at this point, so you know the temperature, you know the temperature, and you know the entropy. So once temperature and entropy are known, all other properties can be calculated. Because for a pure substance, to establish the state, you need to know at least two intensive properties, which comes from the phase rule, which we will discuss in the next class, the phase rule. So once you know temperature and entropy, you can calculate all other properties such as U, H, rho, mu, pressure, specific volume. All these can be calculated since you know T and S. Now once you move into the two-phase region, you have part liquid and part vapor. So both the vapor and liquid are going to have separate properties. So the saturated liquid and saturated vapor. Saturated liquid will have its own enthalpy, which we denote as HL. Saturated vapor will have its enthalpy, HV. Similarly, UL, UV. Now, if you want to calculate the enthalpy, total enthalpy, and you know that vapor fraction, or let us say the liquid fraction is X, what is going to be the vapor fraction? It is going to be 1 minus X. So the total enthalpy is equal to HL multiplied by fraction that is liquid plus HV multiplied by fraction that is vapor. So this is the total enthalpy. Similarly, UT is equal to UL multiplied by X plus HV into 1 minus X.
UV అన్న.
Oh, sorry, right, UV. UV into 1 minus X. Now, let us have a quick look at the phase rule. What does the phase rule state? Phase rule states that the number of independent variables that needs to be fixed in order to establish the state of a system are given by the formula F is equal to C plus 2 minus P, where F is the degrees of freedom. Degrees of freedom. C is the number of components or number of chemical species. And P is the number of phases. So if I say we are in the two-phase region and we are supposed to calculate F, we are in the two-phase region for a pure fluid. What is going to be value of C?
One.
Right, 1. What is going to be the value of P?
2.
2. So what is F? 1. Which means if you say saturated liquid saturated liquid, or for an example, let us take our liquid is pure water. If you say saturated water at 1 atmosphere, that means all other properties are going to be fixed automatically. You don't have to say, so as soon as you say saturated water at 1 atmosphere, the pressure, you have fixed the pressure. So automatically the temperature, the entropy, the enthalpy, the density, the viscosity, all other intensive properties are going to be fixed. So this is what the phase rule says. Let us take another example. Let us say you have. So what do we mean by saturated water? Saturated water means anywhere on this curve. This is the vapor liquid equilibrium curve. So if you say the saturated water, that means it is going to lie on this curve. So as soon as you mention the pressure, the temperature is automatically going to be fixed, because if you say at this pressure P0, you draw a horizontal line. Wherever it intersects the vapor liquid equilibrium curve, if you draw a vertical line, that is the temperature, which is automatically fixed as soon as you fix the pressure. Instead, let us say you have a point here. This is your point. So this is in the vapor region, or also known as the superheated vapor. Superheated vapor. And otherwise, if you have a liquid, this is the liquid region, also known as a subcooled liquid. In these two cases, let us apply the phase rule. Phase rule states F is equal to C plus 2 minus P. What is C for a pure fluid?
1 అన్న.
1. And what is P?
2.
I'm talking about either of these cases. P is 1 because you are saying it is in liquid phase. There are no two phases, there is only liquid phase for this point. Or if you consider this point, there is only vapor phase. So there is only existence of one phase. So P is 1, which means F is equal to 2. And that means you need to fix two properties to establish the state of a system. For example, if you fix temperature and pressure, then automatically enthalpy, U, H, S, rho, mu, all of these are going to be fixed. So you can observe the same thing from the graph. If you need to say tell about the location of a point, you need the x coordinate as well as the y coordinate, which is the same result we obtained from the phase rule. That is, you need to fix the temperature and pressure. Now, does this mean you need to fix the temperature and pressure only? No. It says any two properties. You can give SH, you can give SP, you can give SU or UP in any combination. But temperature and pressure, because they are easily measurable properties, this is the most preferred combination of variables. I hope this discussion on phase rule is clear for everybody.
Yes, and it is clear.
Okay. We will discuss more about the phase rule in upcoming classes. Karun, is this clear, the phase rule?
ఎస్ అన్న, అర్థమైంది ఫేస్.
Okay. Omkar, clear?
ఓకే అన్న.
Okay. Now we will solve the problem. So the problem says you have a turbine. So this is usually the symbol for a turbine. The turbine operates with superheated steam flowing at 1 kg per second. So this is steam, and the mass flow rate of the steam is 1 kg per second. The steam is supplied at, they have given the temperature and pressure. T1 is 441 bar. Sorry, P1 is 441 bar and T1 is 500 degrees Celsius. And they have also given us the outlet. They have said the outlet discharges at P2 is equal to 1.01325 bar and the discharge temperature is 100 degrees Celsius. So, and what data have they given us? They have given us the enthalpy and entropy data. Okay. So the first step is you have to identify your problem. What is the problem about? The problem is about an expander. And second step is what kind of device is an expander? An ideal expander, What kind of a device is it?
Isenthalpic.
Huh?
Isoentropic ana. Entropy same. S1 equals to S2.
Right, perfect. It is isentropic. That is, if an ideal expander is always isentropic. So, what does isentropic mean? As you said, S1 is equal to this S2. Now, do we know the value of S1? Is it given in the data? I think this is a printing mistake. This is 41 bar.
Entropy is given as 7.0785 kilojoule per kg Kelvin.
Okay, 7.0785 kilojoule per kg Kelvin. Okay. Now, do we know the outlet entropy? What should be the outlet entropy?
Same for ideal because it is isentropic.
Because it is isentropic, this also should be 7.0785. But if you look at the data, he has given at these outlet conditions, at pressure 1 bar and 100 degrees Celsius, what is the entropy of saturated vapor?
7.3554 kilojoule per kg Kelvin.
7.3554 kilojoule per kg Kelvin. Right. What is the enthalpy of saturated liquid?
419.1 kilojoule per kg.
Entropy of saturated liquid. Sorry, entropy.
Entropy, okay. 1.3069 kilojoule per kg Kelvin.
1.3069. Now, you need to compare this value. Is S2 lying between the entropy of saturated vapor and entropy of saturated liquid?
Yes,
So
lying.
now they are lying.
So what that means is the outlet stream has two phases in it. It is partly vapor, partly liquid. I hope everyone is clear with this step. You need to compare the entropy of the outlet stream with the entropy of saturated vapor and saturated liquid at the outlet conditions. And if this entropy is lying in between, that means the outlet stream consists of two phases. Let us say, for example, let us say the problem is such that you got S2 is equal to 7.5. Now tell me, is this lying between the entropies of saturated liquid and vapor?
No, no.
So the entropy is greater than the saturated vapor, which means the outlet phase is going to be pure vapor.
Okay.
The outlet phase is going to be pure vapor. Now let us take another case. You get S2 is equal to 1.1. Now where is it lying? Is it less than the liquid, or is it lying in the two phase region, or is it greater than the vapor?
It is less than the saturated liquid.
Which means the outlet stream is pure liquid.
Yes, sir.
So this is an important step. You need to compare the value of S2 with the values of saturated liquid and saturated vapor at the outlet conditions. Now, since our value is in between, we can conclude that it is a two-phase region. Now, do you know how much is liquid and how much is vapor? Like what fraction is liquid and what fraction is vapor? Or can you calculate it?
We can calculate it. X into SV plus 1 minus X into SL equal to S2.
Right, perfect. So you have X into what is SV?
7.3554
7.3554 plus 1 minus X into
1.3069
3069 should
equal
be
to
is equal to
7.07.
7.0785. Now what does X stand for?
Moles.
liquid phase. Mole fraction in liquid.
Think carefully. Is it mole fraction or is it mass fraction? Because all these entropy and entropies, enthalpies given are in mass units. So what will you use? Will you use mole fraction or will you use mass fraction?
Mass fraction.
Right, mass fraction. So X is the mass fraction of vapor or liquid?
Vapor.
Right, vapor. This is the mass fraction of vapor. Now solve this equation and let me know about the value of X. What is the value of X?
Zero 0.954.
Okay. Is everyone getting the same answer?
Yes, 0.954.
Okay. So half of the question is solved. Next, what is the aim in the question? What are they asking us to calculate?
Power.
Maximum power output.
Power output or the rate of work. So, how is power calculated for an expander? So this is the power output. We have seen this in the energy balance for open system. How is W dot calculated? Okay, if the mass flow rate is m dot and the enthalpy of a entering stream is H1 and the exit stream is H2, what is the relation connecting all these four variables?
M dot into H2 minus H1 equals to W.
Right, m dot into H2 minus H1 is equal to W. Now, do you know m dot in this question?
And is given 1 kilojoule, 1 kg per second.
1 kg per second. Do you know H2? Okay, do you know H1?
I think yes, and H1 is given as 344.3.
Okay, H1 is known.
Yes, and 344.319 kg per
Okay,
kilojoule per kg.
okay, very good. Do you know H2?
H2, H2 actually we have two H2s, and one is for saturated vapor and one is
Okay,
for saturated liquid.
okay, so you have H2 liquid and you have H2 vapor.
Yes, and
So which one are you going to take?
so actually we got X no, and so we
Yes.
need to find H2. H2 equals to X into
So
saturated vapor,
H2
enthalpy
is
of
equal
saturated
to
X
H2
into
vapor into X plus 1 minus X into H2 liquid. Is this right?
yes.
Okay. So calculate H2 uh, and substitute in this equation and let me know what is the work you have got.
I'm getting it as minus 909.1655.
Okay, minus 909.655. Okay. So are everybody getting the same answer?
ఎస్ అన్న నియర్ బై -910.2 వచ్చింది.
Okay. Okay, then we don't have the answer. Options లో లేదు కదా ఆన్సర్.
లేదన్నయ్య.
ఓకే. సో బట్ మెథడ్ అర్థమైంది కదా, హౌ టు సాల్వ్ దీస్ ప్రాబ్లమ్స్ అని.
ఎస్ అన్నయ్య.
ఓకే. ఇన్ కేస్ వాళ్ళు ఇఫ్ దే సే ద డిశ్చార్జ్ ప్రెషర్ టెంపరేచర్ ఇచ్చారు కదా మనకి 1 bar and 100 degrees Celsius.
ఎస్ అన్న.
ఇఫ్ దే సే ద డిశ్చార్జ్ ఈజ్ సాచురేటెడ్ వేపర్, అప్పుడు వర్క్ ఎంత అవుతుంది కనుక్కోండి. సో డిశ్చార్జ్ సాచురేటెడ్ వేపర్ అన్నప్పుడు H2 ప్లేస్ లో ఏం యూజ్ చేస్తారు ఇక్కడ?
ఓన్లీ 7.3554.
ఎంత వచ్చింది?
H2 ప్లేస్ లో మనం ఓన్లీ సాచురేటెడ్ వేపర్ దే తీసుకుంటాం కదా అన్నయ్య.
రైట్, H2V ఒకటే తీసుకుంటాము. అప్పుడు ఎంత వచ్చింది వర్క్?
767.9.
ఓకే. సో అది ఉంది కదా ఆప్షన్ లో.
సెకండ్ ఆప్షన్.
రైట్. సో వాళ్ళ క్వశ్చన్ లో దే షుడ్ మెన్షన్ దట్ ద డిశ్చార్జ్ ఈస్ ఎట్ దిస్ టెంపరేచర్, ఎట్ దిస్ ప్రెషర్ అండ్ ఇట్ ఈస్ సాచురేటెడ్ వేపర్ అని మెన్షన్ చేస్తే అప్పుడు ఇలా చేయొచ్చు. బట్ క్వశ్చన్ లో అలా ఇవ్వలేదు కదా, దే డింట్ మెన్షన్ సాచురేటెడ్ వేపర్.
Yes,
So first approach is the right one. Even though it does not have an answer, first approach is the right one. Okay.
Okay, Anna.
And one more question. ఈ ప్రాబ్లమ్ లో did we assume ideal expander?
అన్న మనము సాచురేటెడ్ వేపర్ కనుక్కున్నప్పుడు అయితే ఐడియల్ ఎక్స్పాండర్ అని ఏం తీసుకోలేదు. బట్ ముందు ఆ సిచ్యువేషన్స్ అంటే ఆ మెడివల్ రేంజ్ ఉన్నది తీసుకుంటే మనం ఐడియల్ ఎక్స్పాండర్ అని తీసుకొని మనం మాస్ ఫ్రాక్షన్ అనుకున్నాం అన్నయ్య.
రైట్, ఐడియల్ ఎక్స్పాండర్ అని తీసుకున్నాం ఇనీషియల్ గా, అదే కరెక్ట్ అప్రోచ్. మనం ఐడియల్ ఎక్స్పాండర్ అని ఎందుకు తీసుకున్నాము? వాళ్ళ క్వశ్చన్ లో ఏమి ఇవ్వలేదు కదా ఐడియల్ ఎక్స్పాండర్ అని. మెన్షన్ చేయలేదు. బట్ మనం ఎందుకు తీసుకున్నాము? ఇఫ్ యూ లుక్ కేర్ఫుల్లీ వాళ్ళు ఒక క్లూ ఇచ్చారు. వాళ్ళు క్వశ్చన్ లో పవర్ అవుట్పుట్ అడిగారా, మాక్సిమం పవర్ అవుట్పుట్ అడిగారా?
మాక్సిమం పవర్ అవుట్పుట్.
మాక్సిమం ఎప్పుడు వస్తుంది?
ఒక ఐడియల్ కేస్ లో ఉన్నప్పుడు వస్తుంది.
ఐడియల్ కేస్ విచ్ ఈస్ అ రివర్సిబుల్ కేస్. దట్ ఈస్ ద రీజన్ వీ హ్యావ్ చూజన్ దిస్ టు బి అన్ రివర్సిబుల్ ప్రాసెస్.
ఓకే,
ఇస్ ఇట్ క్లియర్?
yes అన్నయ్య.
సో యూ షుడ్ ఫోకస్ ఆన్ ద టర్మినాలజీ. మీకు డైరెక్ట్గా ఎక్స్ప్లిసిట్గా ఏమి ఇచ్చారు దిస్ ఈస్ అ రివర్సిబుల్ ప్రాసెస్ అని. This is something you have to use logic. When are you going to get maximum power output? You're going to get maximum power output if it is a reversible process. So you're assuming a reversible process. So that's it for today. Any doubts so far about today's class? Karun, any doubts?
No, Anna.
Okay. Omkar? Okay. Karthik?
No, Anna.
Okay. Mallikarjun?
No అనే.
Right. Okay. So quick recap of today's class. What did we study? We studied first law and second law for open systems. So open systems ante mass can get transferred across the boundary. And first law and second law for open systems use chesi we have derived equations for steady state flow devices. Steady state flow devices. What are those devices? There are pumps, there are compressors, there are expanders, there are throttle valves, pipes, etc. So this is for the first and second part lo em chesam, we saw phase diagram and two phase region. Phase diagram and two phase region for pure substances. So these are the two things we have seen. And problem solving chusam. Problem solving for these steady state flow devices. So is everyone clear with these three things we have studied in today's class?
నా
Huh.
టిఎస్ ఫేజ్ డయాగ్రామ్ గీసినప్పుడు ఫస్ట్ ఐ థింక్ సో లో ఎంట్రోపీ ఉన్నప్పుడు సాలిడ్ రాసినావు కదన్నా,
అవును.
తర్వాత సాలిడ్ లిక్విడ్,
రైట్.
తర్వాత లిక్విడ్, తర్వాత డోమ్ వచ్చింది, డోమ్ లో లిక్విడ్ వేపర్, డోమ్ అవుట్ సైడ్ అటు పక్కకేమో వేపర్.
అవును.
కింద ఒక లైన్ గీసినావు కదన్నా, ఆ లైన్ అదేందన్నా అది?
ఓకే మళ్ళీ గీస్తాను. నైస్ క్వశ్చన్. సో ఇది టిఎస్ డయాగ్రామ్లో ఈ లైన్ కిట్ సైడ్ అంతా సాలిడ్. ఈ లైన్ గురించి అడుగుతున్నావా?
అవునన్నా.
ఓకే. ఈ లైన్ ఈజ్ నోన్ యాజ్ ద ట్రిపుల్ పాయింట్ లైన్. వెరీ గుడ్ క్వశ్చన్. ట్రిపుల్ పాయింట్ లైన్ అంటాం. సో ఇక్కడ సాలిడ్, ఇక్కడ యూ హ్యావ్ సాలిడ్ ప్లస్ లిక్విడ్, దెన్ ఇక్కడ నుంచి యూ హ్యావ్ ద డోమ్. సో డోమ్లో యూ హ్యావ్ వేపర్ ప్లస్ లిక్విడ్, అండ్ ఇక్కడ యూ హ్యావ్ లిక్విడ్. సో దిస్ లైన్ ఈస్ కాల్డ్ ద ట్రిపుల్ పాయింట్ లైన్. So anywhere on this line, you will have all the three phases coexist. And below this line, you have solid vapor region. Clear?
ఓకే.
ఇప్పుడు ట్రిపుల్ పాయింట్ లైన్లో కూడా ఇప్పుడు ట్రిపుల్ పాయింట్ లైన్ దగ్గర ద ఎంట్రోపీ ఆఫ్ సాచురేటెడ్ సాలిడ్ ఈస్ గోయింగ్ టు బి దిస్ వాల్యూ. Then entropy of saturated liquid is going to be this value. Entropy of saturated vapor is going to be this value. So identi SS, this is SL, this is going to be SV. So Niku, let us say X is the fraction of solid, you have Y is the fraction of liquid. Then 1 minus X minus Y is going to be the fraction of vapor. In this case, total entropy of the system is equal to SS into X plus SL into Y plus SV into 1 minus X minus Y. Is this clear?
Okay.
And let us also see this. Application of the phase rule to triple point. Now F is equal to C plus 2 minus P. What is the value of C for pure substance? 1. What is the value of P at the triple point?
3.
3. So what is F?
0.
F is 0, which means you don't have to specify any variable. If you say water at its triple point, that's it. Automatically all the properties, pressure, temperature, entropy, enthalpy, density, viscosity, everything will be fixed. So you have no degrees of freedom. Is this clear? Okay. So thank you everyone.
Thanks,
And
Anna.
keep practicing.
Thank you, Anna.
Okay. అందరి దగ్గర యూనిట్ ఆపరేషన్స్ వెబ్సైట్ ఉంది కదా?
నేను తీసుకున్నాను సబ్స్క్రిప్షన్.
ఓకే. యూనిట్ ఆపరేషన్స్ ప్రాబ్లమ్స్ రెగ్యులర్గా చేస్తూ ఉండండి రిపీటెడ్గా. అండ్ యాజ్ సూన్ యాజ్ యూ గెట్ స్ట్రక్ ఇన్ ఎనీ ప్రాబ్లమ్ గ్రూప్లో పెట్టేసేయండి.
ఓకే అన్న, షూర్.
We'll try to solve it. Any subject. We can discuss it in the group.
ఓకే అన్న.
Unit operations is golden material for gate preparation. Best practice you can get is from those problems. Make the maximum use of it. Okay. Thank you everyone. Bye.
థ్యాంక్ యూ అన్న.
Okay, Pujita. Bye. Thank you.